Hello, everyone. Yeah, I'm Harry. Raffael's presenting with me from Barclays. Run the data science team there. We don't have a lot of time, so we might be going at a reasonable pace, but I guess since this is the first technical presentation of the day, you'll be up to it. It's a little bit technical, but then you let yourself in for that. This is some work that we've done thinking about a different similarity metric for recommendations. For example, it can be used beyond that, where we're trying to use the information from an entire graph to create a similarity metric rather than simply looking at similarity of things next to each other, which is what the more conventional metrics do. And the challenge is mainly computational. So we're interested in recommendations in thinking about consumer preferences, in particular latent preferences. So where someone has expressed a preference, it's not wholly interesting to recommend them that preference. We're interested in latent preferences, in other words, things people have yet to express, and therefore when we recommend them, they're doing something incremental to what they might have done before. And our hypothesis in that, because of one of our data sets is about transactions, is that people's purchase choices, the transactions that people make, right, therefore their stated, their revealed preferences imply values on the businesses that they buy from, right? So if you're a price-sensitive person, you shop at price-sensitive places, right? If you're a fair trade person, you're more likely to shop at fair trade kind of places. So we're kind of thinking about latent values of businesses, and that then allows us to think about how similar one business is to another. Most importantly here, we're not actually thinking about enumerating these values, right? So we don't actually need to know that Tesco has price and quality, for example, and Asda isn't, but just that there are a set of values which allow us to think about the similarity of things. Also importantly, apologise for the cough, we are interested in the fact that values can be in some sense propagated through a graph of transactions. I'll talk about a little bit more about what we mean by that, such that if two customers, the yellow dots are customers, the blue dots are shops, are buying from, one is buying from Tesco and Boots, another buying from Boots and Asda, then we can maybe imply some things about Boots from the relative strengths of the things we know about Tesco and Asda. In some sense, that's a kind of iterative process. But if both of the kind of shared shops, Tesco and Asda, are kind of price-sensitive sort of shops, then we can perhaps infer something about Boots in a stronger sense about price than we might be able to imply about quality if only one of the connecting shops is about quality. So it's this idea that transactions imply customer preferences over business values. So this is our data set. I mean, this must be very straightforward for anyone who's sort of seen data. It's a very long set, right, where essentially we say Bob Smith bought from Tesco. We actually don't know what that is, but we just know he bought something from Tesco for a certain amount at a certain time, all the way down. Long, long set. This is a very standard data set for us. Very much of the things that we do think about these long sets. And you might ask, well, how does that relate to the problem that I've just laid out? Well, you can think of transactional data as a bipartite graph, right? Where essentially customers buy from businesses. Where you've bought from a business, there's a link between you, right? An edge between you. Where two people have bought, there are kind of links between them. So we can think about, this is in fact exactly the same information as you've just seen, right? But turned into a graph. And that's sort of what the graph looks like. Customers to businesses. Graphs are all very exciting, people talk a lot about them, but one of the great things about them is that you can go more than one step, right? So you can start saying, well, how is this thing related to this thing, right? Which you can't in a traditional transactional data set. So we were particularly interested in this idea of a graph because of this, the ability of information to pass along the graph, right? Pass through the graph. So that, for example, we have someone from Tesco and some person who buys at Tesco and Boots, someone else who buys at Boots and Asda, someone else who buys at Asda and Lloyd's Pharmacy. That's another pharmacist, a bit like Boots, for anyone who doesn't know it. Boots is a pharmacist. In what sense can we imply things about Tesco from purchases made quite a distance away in the graph, right? That's what we wanted to do. We wanted to be accounting for kind of n-degree separation in our thinking about similarity, right? Going back to this idea of recommendations, it's all about similarity, right? You recommend things that are in some sense similar, but what do we mean by similar? So, forget about the picture here. We went to a thought experiment. We said, okay, what is this metric we're going to think, we're going to create? We need a single metric, single number that can kind of in some sense say, how alike is this thing to that thing? That may be a long way away in the graph. And we came up with this idea of expected degrees of separation, which for some of you will be very straightforward, but I want to introduce a thought experiment which will perhaps help you understand what it is, and importantly, what it is not. So imagine I go to a shop, Tesco, and I have a red token, maybe a big thing, like a paddle, like they have on the underground stations, a red thing. And I take a random customer, and I say to that customer, okay, take this token, take this paddle, and keep it until you go to the next shop you go to, whether it's today, tomorrow, whenever. You just keep it. When you go to the next shop, put a mark on it, and give it to another random person, right? And tell him to do the same thing. So they can then take it to the next shop, put a mark on it, hand it to the next person, and so on and so on. And I will then go and stand at Boots. And the token will arrive, and it will have a certain number of marks on it. And the expected degrees of separation is the number of marks that's on that paddle when it arrives to me. So imagine I did this experiment loads and loads and loads of times. Yeah, I'm working out what the expectation is, or the average, if I'm sampling, right? The average number of marks that I get on that. And that, in some sense, will tell me how far away this is from this, accounting for the fact that there are many different ways of getting from Tesco to Boots in this scenario. Right? And in a graph, you can imagine, so we've got, 1 million different businesses in our graph, which is a big number, big-ish, I guess, with many, many different paths that you can take, some of which are short, some of which are very long, all of which depend on location. Obviously, a shop close by will be close. So this is Tesco in Bristol and Boots in Bristol, right? They have a location element to them. But we are measuring, in some sense, how close those two things are in terms of shared customer preferences. Because why are they linked? Because one customer has bought from both shops. Yeah? So how far are they away in the preference space? That's the idea. The problem is, the challenge is computational.
Yeah. So we basically put our heads on that and thought about how can we actually compute what we just heard in this thought experiment. And turns out that the nice thing with this bipartite graph of customers and businesses is that we can factorize it down into a graph that only goes from businesses to businesses, where the edges of that graph just represent the probabilities to go from one business to the other through all the customers that shop at the two businesses. And through that factorization, we can sort of bring this down in terms of complexity a lot, because we now only have to deal with the 2 million businesses that we have in the UK instead of all the businesses' customer interactions there. So that was the first idea. And now the problem in this graph is that we still have an insane number of paths. So when you think you go from one node to the other, and then you can choose from all the nodes there, and you traverse your way through the graph, there is an exponential number of paths you can come along. And because we were interested in the expectation of this, there's even an infinite number of paths potentially, which we have to. So this made like the actually calculating these numbers exactly very, very hard. But fortunately, there are a few properties in that sort of transition graph that make it a bit easier. So we can see the whole thing as an absorbing Markov chain with some reasonable or not so reasonable assumptions. So basically assuming that the Markov property holds for this graph. And when we do that, the whole thing turns out into to be a discrete phase type distribution. And for these kinds of distributions, we actually have exact analytical solutions. So what you see up there is basically if we partition the graph into a matrix and we then take all the transitions into the upper left part, we can sort of compute the analytical solution for this by taking the inverse of a relatively large matrix. So this is nice, but unfortunately, because we have to take the inverse, is computationally not feasible because it's taking an inverse is O of n to the power 3. And we have to do this for every sink in that graph, so we have to do this n times, so we end up with O of n to the power 4, which is just not happening for even small places. You can sort of try to work around these problems with partitioning the graph, making some, like trying to find links between towns and all these kinds of things, but it turns out to be super, super complex. Okay, so the next approach we thought about was sampling, of course, because we have a distribution, so a natural thing is to go and sample from that distribution. And what we did was, so we went in and tried two different sampling approaches. The first one is just really following along the thought experiment Harry just laid out to you. So sampling loads and loads of paths of potentially very long length, and then calculating the average number of steps that it has taken to get to the shop. The other one is doing something a bit more different with following along the transition probabilities and calculating all the paths to a certain extent. But both of these approaches are computationally feasible with regards to certain parameters. So they are sort of O of n times k times L, where n is the number of shops we have in the network, k is the number of samples we take, and L is the path length. But they come with some extra challenges because we have these insane amount of paths in the graph. It turns out that if you go beyond step 4, you get very big fluctuations because there are just so many paths, and even if you sample a lot, you never be able to estimate the distribution really, really well. So the next thing we sort of thought was to bring it down again to neighborhoods, so a localized EDS. If we cannot actually go beyond 4 with the sampling, why not restrict ourselves to more local neighborhoods, which also has a few extra advantages compared to the global EDS, because what happens when you go shopping is usually a very local decision. So the shops that you shop at, they are in your neighborhood, they're around your workplace, they are very, very localized. It only happens rarely that you go from London to Edinburgh and shop something there. So looking at these sort of neighborhoods made a lot of sense to us, and we used the sampling approach by calculating out the paths of k equals 4 and approximating the distribution like that. And today I have some results from that we did on Bristol. So we chose Bristol because it's sort of a bit more contained city with a bit better defined borders than other towns in the UK. And we ran that on Bristol, which are about 20,000 shops there. And we were interested in sort of how do these numbers compare with this approach to similarity. And what we can see here is, for example, for Asda Superstore in Bristol, what we would expect is some more cheap price preference from the customer, and the shops that are more or less more equal to Asda is like the Container Shop, a Cost Cutter, or the Bling Hair and Beauty, which we would guess are more like cheaper places. What's more what's further away from the Asta is the Mind Shop or the Platinum Pet Food Shop, which are actually quite far away, considering that we only look at a very contained space. So it's basically 3 steps. More than 3 steps is really, really far away in this network. The second one we looked at was Starbucks in Bristol. So what we were seeing there was quite interesting, because Starbucks, people tend to go to Starbucks, other Starbucks outlets basically. So among the top 10, there were loads of other Starbucks places in Bristol, and then also places with a high price preference, more quality preference. But also, interestingly enough, a KFC, which I didn't expect, only 2 steps away. Then more out there, other sort of fast food chains like Krispy Kreme, a fish market far out, or an IKEA. So if you think Starbucks is usually sort of located in the city center, and IKEA is usually far outside of the city center, they are miles apart, and Starbucks people don't go to IKEA, which makes a lot of sense as well. So much for the results. I think that's all we have today, and now I'm happy to take questions.
Wow, we did it. 20 minutes. How about that? Yeah, I mean, I think it's pretty open, right, on this. We you know, there's a lot more we can do with this. We're kind of throwing it out there. We're hoping that people will look at this measure and say, well, we'll have a go at doing something with that as well. We'll probably try and write it up in more detail at some point for people to sort of see how we did it in more detail. But you're welcome to have a go with it if you think that this kind of thing is interesting.
Yeah.
Two questions. One
Okay.
is, the first one is, or are you planning to correlate it with online purchasing as well?
So this can correlate with online purchasing, because remember, the distance, the step is only the step in customer preference, not the actual movement from one shop to another.
But you limited this to local.
Yeah, it's only POS transactions. So only
But there's no reason why it can't be, right?
Right, sure, okay.
We chose Bristol, but if you're thinking about the step, the thing that joins 2 businesses here is customer preference, not actually the journey. Can we have one question? Otherwise, you know, lots of people.
Thanks. Thank you very much for your presentation. I learned a lot. This may be a silly, a basic question. Apologies if I missed it. But can you just explain for me again, or illustrate why Barclays is doing this, and what the current or potential benefit for your customers is?
Yeah. So if we can understand our customers and our customers' values, then we might be able to be better bankers for them. So there's in a lot of industry, there's this whole idea of personalization. And personalization isn't just about selling people more stuff, it's about understanding them. We'd love to be able to get to the point where we're using this kind, if you think about a sequence, well, not even a sequence, a list of preferences or values for each individual, right? Expressed as a list of latent preferences over shops, likes this shop, doesn't like that shop. You've in some sense got a kind of DNA strand of who this customer is, right? Because this customer is a kind of a Tesco-y person, and 50% an Asda-y person, and 30% a Bootsy kind of person. And that's going to be different to someone who's a 100% Body Shop person or something, right? Whatever it is. Those percentages are not meant to add up, right? They're just kind of... That's what it's all about. How can we really know who our customers are? And our idea is that customers imply customer preferences, imply business values, and that therefore some sort of weighted version of those business values is what people are expressing their preferences over, and therefore they're the values of our customers.
I was interested to the data engineering side. Did you use graph databases? If yes, which? Was it challenging to scale? How? If you can tell us something about this.
No, not at all, because we sort of, it's basically just a map of like nodes to other nodes, like an adjacency sort of list. And we used Spark to scale out the whole process of sampling and the computation.
So
I
you
did run it.
broadcast your map,
Yeah.
and then your sampling is distributable.
Yeah. So and we did use GraphX from Spark as well. So we were able to look at this graph and calculate PageRank, individualized PageRank, and all these the other metrics. But no graph database involved at all.
May I continue on the question before? So why Barclays is doing this? So I understand that it's valuable to understand the customer. However, Barclays sells financial products, current accounts, savings, credit cards, mortgages. How this understanding reflects in what you sell, or more precisely, how do you link this?
I get that, yeah, and it's a question that gets asked. So you need to step away, we are trying to step away from the idea that we simply sell 7 products. Loans, mortgages, accounts, whatever, right? We are trying to be, because if we're like that, we're going to get killed by aggregators, right? Who'll just pick and choose and then you're done. So we need to become, right, the financial planning hub for your life, right? And why is that interesting, right? Well, because our team, our kind of little team's motto, right, is that we want to build applications that give every single one of our customers the same level of support and engagement that you would have if you were a billionaire. Right? If you're a billionaire, you don't need to worry about when the insurance is paid. You don't need to worry about how you invest stuff or how you're going to plan for the future. Now, we're a mile away from that, right? But if we want to understand about our customers' needs, not in terms of our customers' need alone, but our customers need a house and therefore might need a mortgage to pay for that. Our customers need to educate their children and therefore might want to think about something. If we want to start thinking about their real needs, we need to think about their values and their preferences in order to inform that. That's where we're trying to go. We're not there yet, guys.
Hi. How big is the sample? How big is the sample data that you have used, and how do you determine that that particular sample data is enough for you to take that use case forward for taking the decisions?
So it varies greatly with the kind of approaches we did. So the town we did this on was Bristol, which was about 20,000 businesses. So the transition matrix we're talking about was 20,000 by 20,000. It's a bit sparse, so we did it in an adjacency list, which makes it a bit easier to distribute. And then the sampling, so it depends on the graph you're using. So you need to sample more if the graph gets bigger because you get more paths. And it also depends on the number of the maximum degree of the nodes you have in the graph. And you can sort of plot out how stable your sampling is and how accurate it actually reflects the actual distribution, and need to adjust to that. And in our case, I think it was about 1 million samples per node, and that was actually quite easy to do with Spark.
I think if you were on the cloud, which we are not, but if you're on the cloud, you would not have a problem scaling out the sampling approach here. Certainly to say 1 million nodes. Wow, I've got lots of questions, man. You have to run away. Cool.
I wanted to ask, how did you capture the customer data? Is it through the API or
they spend on their card. And when you spend on your card, it goes into your statement. You want us to capture that data, mate.
Sorry, you just mentioned that there is quite an obvious correlation between the purchase behavior with the geographical location and the typical journey of the customers. Did you try to normalize your EDS metrics using these correlations? Because that really shows the customer preference instead of their typical journey and where the shops are located. I'm
not sure I fully understood the question, but I'm not sure that that's the kind of question that we should really, why don't we talk about that one-to-one? Because I think that I need to understand a little bit more about what you're asking. There are all sorts of normalizations that were involved, and the big step here is the view that the proportion of customers that go from one shop to another equates to the probability that one customer would go to another. You're just so surprised you've actually eventually got the microphone. You forgot what to say.
Exactly. So going back a little bit to the use case for this, do you see this purely as something that you can use to profile your retail user, like individuals using their cards and offering them products and services, or also something you could use to offer value to the shops, and the brands themselves?
So the brands are our customers as well.
And what kind of actions do you see them taking on this?
We've currently got a product called Smart Business, where we are giving information to small businesses about the businesses around them. So that might well come in there. The big thing, while the microphone's moving, the big thing here is to realise that any set of pairs is a bipartite graph, right? Any set of pairs is a bipartite graph, right? And assuming, once you've then done the Markov, once you've then assumed about proportions to probabilities and the Markov property, you can then kind of collapse that down into a transition matrix, and you can start thinking about degrees of separation across a graph, rather than the kind of classic degrees of separation things like minimum distance and stuff, which are very specific to a single path. What you'll find in shops, you see, is you'll nearly always find one person who shops in both, right? So your minimum distance is no interest at all, particularly where you have hubs in a system, right? Your minimum distance is never going to go more than 2, because as always, you can always go from them to Tesco's to the other shop. It's not going to tell you anything about the between. Sorry.
Hi. Sorry. Is the mic on? Yes. Hi. Sorry. I won't be long. I just wanted to know if you had looked into Bespoke, which was the historical Barclays card application they used to run before and used to capture preferences for customers based on their Barclays card spend, because I'm quite familiar with that from Northampton where I worked on it. So it's very similar, but
Bespoke was more of a classic recommender, right? It was a classic recommender, so it doesn't have a lot of relation to this, because really it's a 1 degree of separation thing. There are plenty of recommenders out there, and you can get them. There's plenty for Spark and that kind of stuff. One more. I'm amazed we've had so many.
Hi. Very simple question. Do you know if there are any other of your competitors that are doing this? And if so, how do you guys...
We've told them about it.
What's that, sorry?
They are now. We've told them about it.
Okay, so how will you guys differentiate yourselves from those guys? How will you, I suppose, retain your customers and gain new customers through what you're doing?
Well, life's competitive, I guess. We'd like to think we're good at what we do. Yeah, I mean, we're not. There's no magic here. You want to copy it? Go and copy it. Bet you can't, but you're welcome to do so. We've told you how it works. We're quite open source, sort of. I'm happy to talk if anyone wants to find out about it.